solve by graphing. I'm going to give you just a second to graph the equation on the screen. Hopefully you remember that you needed to have both of these equations in y equals mx plus b form to be able to graph on a graph. Your solution should look something like this. Y is less than or equal to 2/3 x plus 5, and y is less than or equal to negative 5/4 x plus 7. And since it was less than or equal to for both, we wanted our arrows of shading to go down from both lines. So really our overarching solution is anything that falls in this area down here. All of those are possible solutions to this set of inequalities. Restraints. Our focus for today is on restraints. We're going to be looking at restraints with inequalities and with word problems. Restraints can be placed on the independent x values or the dependent y values for any graphed equation or inequality. So when thinking of inequalities, which y values make the ordered pair 2, y a solution of the inequality represented by the graph below? And so we want to know when our x value is 2, what are our possible solutions for y? Well, let's look at our graph. 2 comes here. From that point forward or higher. So that would be any y value. And we need to look at the line here. We have a dotted line. So the value here, 7, is not included. But any y value that is greater than 7 would be included. Is 4, 5 a solution to the provided inequality? Well, let's check. Let's go over 4. Let's go up 5. Is this solution within the graphed section of the inequality? No, it's not. Hopefully you're seeing how this is going to be a fairly easy lesson for us to get through. Is 4, 5 a solution to the provided systems of inequalities? So again, we want to come over 4. We want to come up 5. Now, we can see that it's in the pink section. It's not in the blue section. It's not in the combined pink-blue section. Remember, our solutions to the systems are all of those answers that meet both equations. So only the solutions within the pink-blue section down here. 4, 5 does not meet that requirement. So no, it would not be a solution to the provided system of inequality. Is -2, -3 a solution to the provided system of inequality? Well, let's check. -2, -3. Well, that's going to be somewhere way down here off the graph, but we can tell that it falls within the designated range. So yes, that would be a solution. Which x values make the ordered pair x, 3 a solution of the following inequality? Well, in order to figure this out, we need to plug in the y value to simplify our inequality. So 4x, and I don't have my pen today, so forgive me, I'm using the mouse to make all of this work, minus 4 times my y value of 3 is got to be greater than 32. All right, so we combine what we have, 4x minus 12 has got to be greater than 32. Add 12 to both sides. 4x has got to be greater than 44. Divide by 4 and x must be greater than 11. So any value where x is greater than 11 would satisfy this ordered pair for this given inequality. Constraints are restrictions, limitations, or boundaries that are used when dealing with word problems. It is possible that solutions which satisfy the equation do not make sense in the context of a real-world situation. So restraints can be placed on independent x values or dependent y values for any graphed equation. Think of items you might graph that would likely have restraints. I'm going to give you just a minute or two to write down a couple. All right, let's talk about what items you have. Did you end up with time? I mean, think about it. If we're talking about time from now forward, do we really have negative time? Can we go back into time? No. We can talk about values prior to current date. But oftentimes when you're talking real world data, that's not relevant. So it depends on what you're talking about as to whether or not it's relevant. And so time would often have constraints. Money would often have constraints. Yes, you can talk about negative value. However, if your word problem has restrictions on how much money you have, you cannot go into those negative values. So for instance, if I had $10 in cash and I was going to spend some money, I could not spend $13. I don't have it to spend, so there would be a constraint there. Product. If I have 4 watches, that's all I have. I cannot have negative 3 watches. It's not a possibility. So there is a restraint there, or a constraint there. Energy. Now, if I have a designated amount of energy, I can't go and just get more energy. It's got to be produced. So energy might have constraints. Distance. We've already talked last year about how distance is always positive because we never go in negative distance. Now, certainly we could talk about a time where we went a distance prior, but it's not really negative distance. So distance could have constraints. Grades. Well, think about what constraints your grades might have. When's the last time you saw a negative 30 on your report card? It doesn't happen, does it? Now, certainly you could have a 0. You didn't do anything. You didn't earn anything. Well, what about a 1,000 on your report card? Just doesn't happen, right? There's a constraint on that system. And so when we're talking about grading, we have a max of 100. A max of 100 is what go in the grade book. Even if you did the extra credit and you did all the extra assignments and you had 103 in the grade, at some point in time when we report your grade, it's going to have to be a max of 100. It just can't be reported higher than that. Time is typically not referenced as negative. We talked about that just previously. So since time is not reported as negative, which graph makes sense to use? Yeah, that's right. The graph on the right. We only need to worry about quadrant 1 if we're not referencing a negative value for time. So this is where you can allow your restraints to help restrict how much you need to graph. You have quarters and dimes totaling $15.50. Altogether, you have at least 95 coins. What constraints are present in this problem? What solutions or solution can we find? Go ahead and think about this problem for just a minute. What constraints are present in the problem? All right, we have at least 95 coins. So that means I could have more than 95 coins, right? Well, could I have 1,000,000 coins? Not really, right? It wouldn't be possible to have 1,000,000 coins because if I had 1,000,000 coins, I would have more than $15.50. All right, what about 100? Well, even 100 quarters is going to exceed the $15.50. So there are some constraints on how many quarters we can have. There are constraints on how many dimes we can have. There's constraints on how many quarters we must have. Like I can't go into a negative 30 quarters, right? It just doesn't exist. You don't have a negative 30 on a quantity of something. And so those are our restraints. Now solutions, what solutions can we find? Well, our solutions have got to be greater than a particular value, but they also need to fall within the range of our number line because our number line is our red line. Our red line represents our equation, quarters and dimes totaling $15.50. So as long as our blue solutions fall within the red line, they should add up to $15.50.